Hey folks, this is Dave Caudell, graduate student with Dr. Berger's group at Fisk University, and today I'll be covering some of the basics with our atomic force microscope, or AFM. This is an ANOVA scanning probe microscope, which we'll use in tapping mode today, and our group has had this AFM since 2007. To start, we turn on the NanoDrive. While our software boots up, we remove the protective cover of the AFM. Swivel the microscope out of the way to gain access to the stage. To remove the stage mount, you must first unplug it. This is accomplished by squeezing both sides at once and then gently pulling it free. Then, to remove the probe mount, lift it by first tilting it towards the back of the stage, then lifting it clear. The probe mount should be placed upside down on the table. Hold the probe mount firmly as you pull the probe brace free. This brace holds the chip that your cantilever is mounted to. This is the tool we use to release the chip from the probe brace. Place the teeth between the chip and the spring, then, with one hand, push both the brace and the tool flat on the table. As you lift the chip free, be careful not to touch the cantilever. This cantilever is for tapping mode, distinguishable by its two blue strips. To load a chip, we reverse the process. Remember, the cantilever is very fragile. The slightest touch of your finger will break it off, so you must be careful not to touch it at any point. To ensure that the chip is mounted properly, gently rock it back and forth. When you place the chip brace into the probe mount, you should feel it click into place. To test that our AFM is working properly, we're going to use calibration grading with a pitch of 1 micron. When placing our sample onto the stage, it is held in place by magnets. Be careful not to let the force of the magnets slam the sample onto the stage, as this can damage our piezoelectric motors. Note that we rotate the sample to align with the stage. This ensures that our scan of the grading is even. Now we place the probe mount back into position. Take note of the 3 points that it fits on. Again, we start with the back point before resting it on the front two. This helps to ensure that our cantilever does not bump the sample. Once in place, we gently rock the mount to ensure it's well seated. We plug the mount into the stage, and then we'll swing the microscope back into place. We're now ready to start the program and scan the sample. In the Windows bar at the bottom of the left screen, click the second icon to start the NanoDrive 8.1 software. Once the software loads, we come to the system configuration. Ensure that tapping mode is selected, that we're on default for experiments, and the linearized large area scanner is selected. Then click Load Experiment. Once the program loads, click this icon to expand the window to take up your left screen. On our right screen is our microscope video feed. This slider controls the illumination of the sample. And we can zoom in and out with these icons. The bottom knobs on the AFM control the positioning of the microscope. The side knob is the vertical control, while the front knob is the horizontal control. The upper knob on the side controls the focus of the microscope, with the larger ring for coarse and the smaller ring for fine focus. Using these controls, we center in on the tip of the cantilever. We're adjusting the focus to demonstrate a common mistake for new users. Given the mirror-like surface, it is possible to focus on the reflection of the cantilever rather than the cantilever itself. Now we're ready to align our laser, so we'll lower the illumination to see the laser better and zoom in on the cantilever tip. On our stage, the upper right knob is for shifting the laser up and down, while the one below is used for side to side. We use these controls to adjust the laser spot on the end of our cantilever. Note that the laser spot is as wide as the cantilever itself and where we place the spot. Now we need to center the diodes. Click the second icon to bring up this window. The controls to adjust the diodes are on the left side of the stage. Note the indicators next to the knobs. The 4 red lights show where the laser is off-center. Once our laser is near the center, we can turn our attention to the program. Within the laser alignment window, there are two sets of green numbers. The side reads the difference in power from the left and right side of the vertical line, while the top is the difference between the top and bottom of the horizontal line. Since we're using tapping mode, we need to tune the cantilever. Click the third icon, the one that looks like a tuning fork, to bring up our cantilever tuning window. Set the range from 0 to 1000 kHz, then select Auto Tune. Adjust the target tapping signal to 5 volts. A tip to remember with this software: when typing in a new value, you must hit Enter for the program to accept it. Push the play button, and the software will automatically tune your cantilever. These cantilevers should have a frequency around 300 kHz, and if your frequency is too far off, this could indicate a problem with the cantilever. Take note of this frequency profile. This is a new tip, and a good tip should have a profile similar to this. If the profile looks very different, you have a bad tip. Let's compare this profile with one for a bad tip. As our AutoTune program runs, we immediately see that the shape is different. The tip of our probe is broken off, throwing off the resonance of the cantilever. Here's our good profile, and here's our bad profile. We're now ready to approach our sample, so we close the tuning window and focus our microscope on the surface. Our focus should be between the cantilever and its mirror image. This calibration grating has some specs on it, so we focus on those. Click the fourth icon, the one that looks like gears, to open our motor stage controls. These up and down buttons lift and lower our tip to the surface. Never use these controls if the tip is in contact with your sample. As we approach the surface, keep an eye on the stage itself. The goal is to get close without actually touching. We can also watch the microscope. As the tip approaches the surface, it comes into focus. Remember, we don't want to actually touch the surface, just get close, so don't bring the tip completely into focus or it will touch the surface. Click the Engage button, the fifth icon shown here, to bring the tip into contact. In this example, I forgot to adjust the set point, and there seems no way to stop this bad approach from happening. To trick the software into stopping the auto approach, I changed the set point to a value higher than the feedback. This tricks the software into thinking the tip is already engaged and canceling. The software signals an engaged tip with this message to the right. This is also indicated by a green bar beneath the Engage button. To disengage our tip from the surface, we need to click this button. This is the only way you should ever lift a tip from the surface. We will now approach the surface properly. Note the feedback value, shown here at roughly 4.8 volts. Adjust the set point to roughly 3/4 of this value, or simply 1 volt less. Remember to always hit Enter for the program to accept your changes. We have now clicked the Approach button, and we wait for the tip to engage. Once the tip is engaged, the scanning control window opens. Click Channels in the menu of the scanning control. This brings up the Acquire window. Ensure that the first 4 options are the only ones selected. There are several parameters listed in the scanning control window. Samples per line sets the resolution of your scan and is currently set to 256 data points. This will give us a 256 by 256 image. The scan rate sets the speed at which the tip travels over the surface. With a scan range of 3 microns and a scan rate of 1 Hz, this means that the tip will travel 3 microns down and 3 microns back in 1 second. So our tip is traveling the surface at 6 microns per second. Never let the tip travel faster than 20 microns per second. Not only will this lead to inferior images, it will shorten the life of your tip. For our scans today, the scan range will be set to 10 microns and the scan rate will be set to 0.5 Hz. We click the Play button in the scanning control window to begin scanning. In this example, our tip is not in good contact with the surface, and we see that the forward and backward height data do not match. We need to press a little harder with our tip, so we lower the set point as we watch the scan. The difference between the feedback and the set point measures how hard our tip is pressing into the surface. Once I've found a minimum amount of pressure for good data, I restart the scan at that set point. With each pass, our data refreshes. The graph, updated as we scan, shows our forwards and backwards height data. Note you can also see the motion of the sample in the microscope. As our scan progresses, we can see 2D images of our height and tapping amplitudes. To improve the contrast of these images, click the Auto option in each window. Notice the height data is tilted as we scan. To adjust this, there's a drop-down menu in each window. Select the 2D plane fit to artificially flatten the image, which will give you a better view of your data. Although tapping amplitude does not give usable data for height analysis, viewing it as you scan helps to determine if there are any artifacts or errors in your scan. Once your scan is complete, return your adjustments to None. The 2D plane fit alters the data, and there are better ways to level your data that are not available with this software. When saving your data, create your own folder. This folder can be found under My Documents inside Veeco Capture. When naming your data, it is handy to include some of your AFM settings in the name of the file. In this example, I used a bad tip on the calibration grating, with a scan range of 10 microns and a scan rate of 0.5 Hz, and I've included this information in the name of this file. I also note that this data was taken in tapping mode. I click the withdraw icon to lift the tip from the surface. Just to be safe, I typically do this 2 or 3 times. Note the info window in the upper left now reads Withdrawn, and the bar beneath the Engage button is red. In the microscope, we can see how high each click of the withdraw button lifts the cantilever. We now use the motor stage control to lift our cantilever the rest of the way. As you lose focus on the cantilever in the microscope, you can turn and watch the stage as it ascends. Make certain the cantilever is at least 5 millimeters from the surface of your sample before stopping. Another user may have a taller sample than you, so we wish to give them plenty of room to work with.